In this video, we're going to talk about L'Hopital's rule. L'Hopital's rule handled cases such as this, where you have the limit as x approaches 0, and you have like two functions, one divided by the other, and the limit is 0 over 0 or infinity over infinity. And there are several other cases where you would use L'Hopital's rule to handle this kind of a problem. And so, for example, if you want to find the limit as x approaches 0 of e to the x minus 1 divided by 4x, this is going to give you e to the 0 minus 1 for 0. This is going to, of course, be 1 minus 1 over 0, which is 0 over 0. We can use L'Hopital's rule, which says we can take, instead of this, take the limit as x approaches 0 of the numerator, derivative of the numerator divided by the derivative of the denominator like this, and find that limit. And so in our case here, the derivative of the new e to the x, so give the limit x approaches 0, derivative of this is going to be just e to the x minus 0 divided by 4. So I took the derivative of the numerator divided by the derivative of the denominator, and now put in our 0. There'll be e to the 0 over 4, which is equal to 1/4. That's one simple example of how to apply L'Hopital's rule, that if you get 0 over 0 or infinity over infinity, you can take the derivative of the numerator, divide by the derivative of the denominator, and then put those limits in and see what you get, and that will be your limit. Now, it's important to note that you can't always just apply L'Hopital's rule without having these conditions, like without having 0 over 0 or infinity over infinity. So let's take a look at this theorem that shows one case in which we can use L'Hopital's rule. Let f and g be defined on AB, and let f of A equals g of A equals 0. And let g of x not be equal to 0 for x from A to B, if f and g are differentiable, at A, and g prime of x excuse me, G prime of A is not equal to 0, then the limit of F over G at A exists and is equal to F prime of A divided by G prime of A. That is the limit as X approaches A from the positive side, F of X, G of X is equal to F prime of A divided by G prime of A, like this. So it's sort of a mouthful, but let's know several things. F and G are defined on the interval AB, and F and G at A are both 0. So we're going to have 0 over 0, and let G of X not be 0 between A and B. So even though the functions FA and GA are 0 at A, at any point greater than A and below B, G of X is not 0. F and G are differentiable at A, and G prime of A is not 0. Then the limit F divided by G at A exists and is equal to the derivative of F of A, excuse me, the derivative of F divided by the derivative of A given this way. So again, for this particular theorem, an important thing that we need is that F of A and G of A have to be 0. So let's take a look at this, see if we can prove this. So let's begin with this proof. First of all, let's write this quotient F. Write it down here. So let's write F of X over G of X this way. F of X over G of X. Now we can subtract 0, of course. So notice one of the conditions we have for our theorem is that FA and GA are both 0. So we can always add or subtract 0 whenever we want. So let's subtract F of A here and G of A here, since they're both 0. So it's a critical point. Let me just note that GA equal FA or 0. So that's a critical point here. Then also, we could multiply the numerator and the denominator by X minus A. So we're just multiplying by 1, which of course we're allowed to do. Like this. And then let's just rearrange this a little bit. Like this. And so now, so let's just rewrite. We have f of x divided by g of x equal this. So let's just write this down here to make this a little bit neater. F of x g x equals f x f a x minus a g x g a x minus a, like this. So that's all I did. I just rewrote what we had up here, make it a little bit more concise. Then now let's take the limit of both sides. Limit is x approaches, let's say a from the, let's say from the positive side. Since we defined a to be, our function was between a and b, so let's approach it from the positive side. And then, so we're going to have here is the limit as x approaches a, and the limit as x approaches a here. And of course, what we have, what is this? This is the definition of the derivative. The derivative at a. This is f prime of a divided by g prime of a, like that. So in other words, the limit of fx over gx is equal to the derivative of f divided by the derivative of g. Again, one very important step here is we needed to have GA and FA be equal to 0. Otherwise, we couldn't do this first step here. And that first step was critical to getting this to the form we could get the derivative. Next, we're going to introduce the Cauchy mean value theorem. And let F and G be continuous on AB. And differentiable on AB, the open interval, and assume that G prime of X is not equal to 0 for all X in AB. Then there exists a C in AB such that FB minus FA divided by GB minus GA is equal to F prime of C over G prime C, like that. So that's the Cauchy mean value theorem. You have two continuous functions. They're continuous on AB, differentiable. Assume the derivative of G is not zero. Then for all X in AB, there exists a C in AB such that this is true. We're going to use this a little bit later. Now we can state the actual L'Hopital's rules. And the proofs are related to the theorems we had just mentioned. That this go from A, B infinity. And let FG be differentiable on AB such that G prime of X equals 0 for all X AB, and suppose that the limit as X approaches A from the positive side, FX, the limit A GX is equal to 0, then if the limit at X approaches A from the positive side, FX GX equals L, and L is in the reals, or L is equal to negative infinity or L equal infinity. Then the limit as X approaches A plus F of X, G of X is equal to L. So once again, what it says is if you have a function that's differentiable and the derivative of G is not 0 for all X in the interval AB, but the limit of F of X and F of G are both 0, then if the derivative of Fx divided by the derivative of G of X is equal to L, and that is a real number, or it's negative infinity, positive infinity, then the limit of this fraction is going to be the same as the limit of the derivative. Very similar to what we said in the previous theorem, though you can extend this to A minus, approaching A from the minus side in these cases. Once again, though, we need to have that the limit of these two have to approach 0 to apply this. Then we have L'Hopital's rule 2. let negative infinity AB less than or equal to infinity, and let F and G be differentiable on AB such that G prime of X is not equal to 0 for all X in AB. Suppose the limit as X approaches A from the plus side of G of X is equal to plus or minus infinity, then if the limit as X approaches A from plus side, F prime of X over G prime of X equal L, and L is in the reals, or L is negative infinity, L is positive infinity. Then the limit as X approaches A from the positive side of Fx over Gx is going to be equal to the limit. So once again, this deals with a case where we have the denominator only approaching positive or negative infinity. Now, when I say only, the numerator could approach positive or negative infinity, but this is the case where at least the denominator approaches positive or negative infinity. Then we can take the derivative of the numerator divided by the derivative of the denominator. If we get a limit or it approaches negative infinity or positive infinity, then the limit, this limit here, will be equal to the limit of the original quotient, like that. Let's take a couple of examples from the text. So let's consider this. The limit is X approaches infinity of log of X divided by X. You can see that this is going to be infinity over infinity. And so we can apply L'Hopital's rule. And that's going to give us the limit as X approaches infinity of 1 over X divided by 1. Here in the numerator, this denominator goes to infinity, so this whole fraction will go to 0. So we have 0 over 1, which is 0. So again, here's an interesting one from the text. The limit as X approaches 0 from the positive side, and you have log of sine x over log x. And you can see, of course, if you plug 0 into here, that's going to go towards negative infinity. And then this is going to be the log of 0, which again is going to be negative infinity over negative infinity. So let's take a look at that. Apply L'Hopital. Limit x approaches 0. Now the derivative of the numerator will be 1 over sine x times the derivative of the inside, which is cos x. Then we're going to have just 1 over x here in the denominator. And so let's see, where does that take us? Let's rewrite this a little bit. So it's going to be x cos x divided by sine x. Once again, we're going to get, this time we'll get 0 times 1, 0. So we're going to get 0 over 0 again. So let's try to take another derivative here. Take a derivative of that product. The limit is x approaches 0, derivative to the first times the second minus the first times the derivative of the second. Excuse me, plus the derivative of the second. We're just doing the product because we're just doing the numerator. And then just do the denominator, cos x. So what do we have this time? This time we're going to have 1 times 1 plus 0 over 1. Looks like the limit is 1, like that. So there we had to apply L'Hopital's rule twice. Let's take a look at another problem. So suppose you have the case where you have infinity minus infinity. So let's say you have a case like this. What do we do with this case? Usually, the way we handle this is we kind of bring the two terms together, usually with a common denominator. So let's take a look at that. And so let's consider the limit as x approaches 1. 1 log x over 1x minus 1, like this. And so notice what we're going to have here. We're going to have infinity, because we're going to have, as log goes to 1, this will end up being like 1 sort of approaching 0. And over here, it'll be 1 minus 1. That's approaching 0. And that's going to be sort of infinity minus infinity like this. So let's see if we can handle this. So again, the best way usually to handle this is to find the common denominator. And if we multiply this one by x1, excuse me, x minus 1 over x minus 1, multiply this by log over log, we're going to get something like this. So after we make a common denominator by multiplying this by x over 1 over x over 1, this by log over log, and put these together, we get this. And so let's see what happens now. Once again, this is going to be 1 minus 1 minus, we put 1 in here. That's going to be log of 1 is 0. Then 1 minus 1 log of 1 is 0. So we're going to have 0 over 0. So we can apply L'Hopital's rule. And so let's take the derivative of the numerator. And we're going to have 1 minus 0 minus 1 over x. And we're going to have a product in the denominator. So be the derivative of the first times the second plus the first times the derivative of the second, like this. And let's see what we have now. This is going, let's multiply some things out here. Limit as x approaches 1, 1 minus 1 over x, log x. And this is going to be 1 minus 1 over x. And we put our 1 in here. We have 1 minus 1. Log of 1 is 0. Plus 1 minus 1, which is 0 over 0 again. So we're going to have to apply L'Hopital's rule again. Apply it here. Take the derivative of this. Derivative to the numerator. That's, of course, that's going to be 0. Then when we take derivative of this, that's going to be, that's like x to the minus 1. So bring the minus 1 forward, makes that positive. And that'll be x to the minus 2. Then we can write it that way. And then take the derivative of the denominator. That's 1 over x. And over here, that's going to be plus 0. And then this is going to be similar to the numerator. It'll end up being a negative 1 over x squared. Once again, I'll make that positive. There'll be 1 over x squared. Put the numbers in 1 over 1, 1 over 1, 1 over 1 squared equals a half. That was not an expected result. And that's an interesting problem. Again, this problem was from Stewart. So that's usually what you do when you have infinity minus infinity. Put the terms together and apply L'Hopital's rule as needed. Here we had to apply it L'Hopital's rule twice. Another case is the infinity times 0. And so let's take a look at that. And so this is going to be, let's notice this one here. Let's say as x goes to infinity. So we're going to have infinity over here. And then e to the negative infinity. That's like having something like this. So that's going to go to, this is going to go to 0, and that's going to go to infinity. So we have like infinity times 0. And usually the way you handle this is to kind of rewrite these so that we either have infinity over infinity or 0 over 0. So let's see what we could do in this case. So usually we want to somehow put one of these in the denominator, and it really could be either one. In fact, we pretty much have it right here. So let's rewrite this. Limit x approach to infinity of x cubed over e to the x squared. And then notice here, we're going to have infinity over infinity. And then we can use L'Hopital's rule. Take the derivative of the numerator. Divide by the derivative of the denominator. And when things cancel here, we'll end up with 3x over 2 e to the x squared. But now we're still going to have infinity over infinity. So let's apply L'Hopital's again. Derivative of the numerator divided by the derivative of the denominator. Once again, it'll be 2 let me just check. Yes, that'll be 2. Excuse me, 4. 4x e to the x squared, like that. And this is going to be 3 over infinity, and that's just going to be 0. Now, let's take a look at this problem from the text. This is the limit as x goes to 0 of x to the x. So once again, this is an indeterminate form. This is going to be 0 to the 0 power. So this one's undefined. So let's take a look at this. And so we have 0 to the 0. Now what we can do is, there's sort of a trick on something like this. We can rewrite this as e to the log of x to the x. That's going to be equal to the limit of ex to the log of x, like this. And then the question is, what is going to happen here? Because here, this is going to go to negative infinity, and this is going to go to 0. So here we're going to have 0 times negative infinity. So we're probably going to have to look just at this exponent here. And of course, what we can do, we can rewrite this as the limit as x approaches 0. And this is going to be, excuse me, we can do actually since all the variables with x, they're all in the exponent. So let's write this as e limit as x approaches 0, x log x like this. And now let's focus on this here. Like I said, we have 0 times negative infinity. We can maybe rewrite this. And let's try it. Let's try this. Let's rewrite this as the limit as x approaches infinity as x over 1 log x, like this. And so this is going to give us e, that's going to be 0 over 1 over negative infinity, which that's going to basically be 0 in the denominator. So that will give us 0 over 0. Now we can apply L'Hopital's rule to that exponent. And so we can do this here. This would be e, and the derivative of the numerator would be 1 derivative of the denominator. Now this gets a little bit tricky here. So this is going to be like a quotient rule. So this will be derivative of the top times the bottom minus the top times the derivative of the bottom, which is 1 over x, all over the bottom squared. And let's see if we can rewrite this as limit x approaches 0 from the plus side. This is the log of x squared, and this is just going to be 0. So this is going to be negative 1 over x like this. And so now we're going to have, this will be negative infinity. This is going to be also negative infinity. So I don't think this is going to work. So let's try, let's skip this one, and let's go back to this over here, right here where we rewrote this here. Let me do that a little bit differently. Let's try to do it this way. Let's put the 1 over x into the denominator. Like this. And so we're going to end up getting e And this will end up being negative infinity over infinity. Once again, apply L'Hopital's rule to the exponent. And so take the derivatives. Derivative of the numerator is going to be 1 over x divided by negative 1 over x squared like this. And we should have to have a limit in here. And bring this in the numerator. And we'll have the limit approaches 0. Then it's going to be negative x like this. So now when we approach 0 from the positive side, this is going to be a negative here. So that's going to be e to the 0, or the negative 0, which is going to be 1. So often we have two choices when we get to something like this. When we have 0 times infinity, we could either put this in the denominator like we did here, or put this in the denominator. Often one is solvable, the other one is not, so you often have to try it both ways to find one that will work.